Welcome to this video on statistical mechanics. My name is Jos Thijssen and I have made this movie for my students in the Advanced Statistical Mechanics course, which is part of the Applied Physics degree course. It's a master course at Delft University of Technology. In this movie I want to go into the van der Waals theory for phase transitions, and in order to appreciate all the steps it's necessary to first go a little bit into the Legendre transformations as they are applied to thermodynamic potentials in order to study their convexity and concavity properties. I hope it will be a useful movie. So to start, I would like to go into the Legendre transformation, which plays such a very important role in thermodynamics. So I perform here a Legendre transformation for a function of one variable, which is fx, and let us assume that this function f of x is a concave function, which implies that the second derivative of f is negative. We can then perform a Legendre transformation which transforms f into a function of g, which initially has two arguments, x and y, and it's defined as f, which was a function of x minus x times y. And then we calculate g exclusively as a function of y, as the maximum of this function is a function of x. So what we do is we take the derivative of this function f primed x minus y is 0, and therefore we find that y should be the derivative of f at x. Now it is interesting to see whether the new function g of y is also concave or whether it's convex. And in order to do that, we look at dg, which is a small variation of the function which depends on x and y. So we have a contribution from x dx. So we have f primed x times dx, and then from this term we have a dx times y, and we have an x times dy. So that's the variation due to a change in y. So what we conclude is, first of all, f primed is equal to y when we go to the real Legendre transformation. So these two terms drop out, and so the only variation that is allowed of g is the one minus x times dy. And having that, we find that dg dy, just be divided by dy, is equal to minus x, and therefore the second derivative of g with respect to y is the same as minus the derivative dx dy. Now this derivative is 1 over dy dx, but y was the first derivative of f, so that means that this is minus 1 over the second derivative of f. Given the fact that the second derivative by assumption was negative, concave function, we see that then the second derivative of g with respect to y is positive. So g turns out to be a convex function. Had we assumed that f was a convex function, then we would have found that g is a concave function. So generally we can say that the Legendre transformation turns a convex function into a concave one, and vice versa. So we start by repeating that very conclusion. A Legendre transformation turns a convex function into a concave one and vice versa. So let's illustrate that using some functions from thermodynamics, some thermodynamic potentials. So we start by the energy, which is a convex function of the entropy, the volume, and the particle number. So these are all extrinsic variables. And from the energy we can replace the s using a Legendre transformation and turn it into a variable t, but that means that we transform from E, the energy, to the F, the free energy. Then F, because we have performed this Legendre transformation, E was convex as a function of S, so F must now be concave as a function of t. We didn't do anything to the variable v, so F is still a variable of a function of v, and it's a convex function of v, because we didn't transform v. Now we can do the transformation once more. Then we transform v and we trade it in for the new variable P, which is an intrinsic variable, so volume is replaced by pressure, and this is the Gibbs free energy. And then again, G is a concave function of P. So the fact that there is a plus sign here doesn't change that conclusion, as you can verify easily. Now, it is interesting to see whether we could perhaps write this as a function not of P, but as a function of P and V. So there is a certain equilibrium value of V, and that equilibrium value is found from the thermodynamic relations that we obtain from G, but it doesn't mean that this is the only value possible. So in principle we could imagine that even with P constant, like when I have a piston with a fixed mass and it can move, keeps the pressure constant, but there may be fluctuations in the volume, and in that case these fluctuations can be characterized also by a Gibbs free energy, but that's the Gibbs free energy for which we do not require that the P that we put in there is the derivative of F. With respect to V at constant T and N. So we relax this condition. If we then consider for fixed P the behavior of G as a function of V, well, G is then a convex function of V, which means that it has a minimum, and indeed the minimum is achieved at equilibrium. And so every time we have a change in V due to a fluctuation, then the Gibbs free energy goes up. So let us now look at a particular example. I have just chosen a simple function f as a function of V and of course of T and N, but they are less important because we focus on V here. And it's alpha times V minus V0 squared plus beta. Alpha is positive, so it has indeed a minimum as a function of V. And alpha and beta, they may depend on T and N, but from now on we will not mention T and N because they will always be fixed. And the Gibbs free energy G is then defined as a function of P and V first, and then we have that it is equal to F plus PV. Now if we are at equilibrium, then we know that G will achieve its minimum as a function of V. So we look for the minimum as a function of V of this expression here. And if we do the math, we can find the value of P from the condition that this function should be minimal. We put that back into this function, and then we get a function which exclusively depends on P. So it's a concave function. Note that the V0, it's just a constant. And this is a concave function. Now the function f, you can find that here. This is the function f. It's the same as the function here. When we take P is 0, then we find V. So I can identify the boundary of this surface with the function f. Now considering the function g, which depends on p, that is the red curve. So the red curve is a function of p, as you can see, and of course for each p we have a different minimum, so we see also that the v shifts a little bit, but the v, once we fix p, then v is also fixed, and that's why we are now on the red curve, which as you can see is a concave function. It is a function which has a maximum. The free energy was convex because it has a minimum. Then finally we look at the g as a function of p and v, but now we fix p. So I will indicate that by, for example, a subscript 0. We take p equal to p0, and in this case it's taken to be 5. And then we can consider it as a function of v, and you see that this function again has a minimum. So g is a convex function as a function of v. Finally, it is interesting to look at the meaning of the fact that g is a concave function as function of p. We know that dg dp at constant t and n, that is v. And therefore, if we look at d squared g dp squared at constant t and n, that is equal to dv dp at constant t and n, and because g is convex, that should be smaller than 0. And that makes sense. If we increase the pressure, the volume goes down, so the dv is opposite to the p, and it is therefore very highly natural that this quantity, which is related to the compressibility, is negative. Compressibility is always negative. We start by something we know very well, and that's the ideal gas law, which is P times V is NkBT. And that law that holds for particles that do not interact, so the particles do not feel each other. That's of course not realistic. In the realistic case, the particles feel an interaction which has more or less this form. So here we see the two-particle interaction, which only depends on the distance between two particles, that distance is r, and we see that if the particles get too close, there is a high energy penalty which expresses itself into this positive potential. Also we see that the potential can become negative, so that's if particles are just beyond the hard core region. And so we see that there is a repulsive core. That repulsive core, well, we express that in terms of a volume, and that volume is called 2b. The factor of 2 is just convention, and that reduces the volume available to the particles. So let's first look at particles without interaction and see how we can calculate the ideal gas partition function. Well, that partition function is a sum, so in this case it's an integral over all the momenta of the particles and all their positions. The positions integrate quite easily because the volume for each particle is just v, and we have n particles, each moving in a three-dimensional volume, so that gives me simply v in the power n. The kinetic energy that factorizes this integral factorizes in 3n integrals that are all identical. They are Gaussian integrals and they can be calculated analytically. And in the end that gives rise to a 1 over lambda to the power 3n. That is when I combine it with this vector of h, which is the volume, the minimum volume I have in phase space for a PQ pair, and there is a factor n factorial which takes into account the indistinguishability of the quantum particles. So if I calculate the ideal gas free energy, that is minus kBT ln z, and from this expression here it's very easy to calculate that. Just take the logarithm and put a minus kBT in front, and if I then calculate the pressure, which is given by minus the ideal gas free energy, then taking the derivative with respect to V at constant temperature and particle number, I get my equation of state, my ideal gas equation of state. So what changes when we switch on the interactions? Well, the interactions only depend on the positions of the particles, so it's only this part of the integral which will be affected by the interactions. And so this integral is now replaced by this integral, which has now a possibly complicated integrand, there is a minus beta u, which gives you the potential energy, and usually we assume that the potential energy can be written as a sum of two particle interactions. So these are pair interactions, and I sum over each pair once. The v here is a function, and that you should think of that function as this curve here. I've drawn here the Lennard-Jones curve because you can show that for neutral particles which are spherically symmetric, they can attract each other by a van der Waals dispersion force, and that has a dependence of 1 over r to the power 6th. And for convenience, then we often use sigma over r to the power 12 for the repulsive part, although that's not really essential, as long as it is repulsive. Well, as I said, each particle will reduce the available volume for the next particle by a excluded volume 2b. So you should think of a particle being here, and then another particle is not allowed to get too close because of this repulsive interaction, and the volume that is excluded is called 2b. So instead of the v to the power n that we get in the ideal gas, the best way to calculate the new expression is to first assume that we put one particle in the volume, so that has a volume v at its disposal. The second particle, however, has only a v minus 2b available, and then v minus 4b, etc., etc. And the last particle, that's particle number n, has only v minus n minus 1 times 2b available. And so if we then take that logarithm of this product, we can write it as a sum of logarithms, and then assuming that the excluded volume is small with respect to the volume of the container, we can approximate this by, say, the average value of the terms here. And the average value is when we take here n equal to n over, instead of n we have n over 2. So then we are somewhere midway between this term and that term. Well, n or n minus 1 doesn't matter if we have many particles, and so we arrive at n times the average interaction part, and that's the logarithm of v minus nb. In order to approximate the attractive part, we just look at one particle immersed in the gas or in the liquid. So that particle has n minus 1 partners with which it can interact, and the interaction is given as a normalized integral of the interaction potential of this single particle and its neighbor, and it's normalized by dividing by v. Obviously this integral has to be carried out only over the excluded volume, and so you may argue that indeed we should put here also a minus n minus 1 times 2b, and that can be done, but that gives you only a higher order interaction in the end, so it turns out that this extra correction is not relevant. Anyhow, we call this integral, so the integral over v divided by 2, that combination, we call that a. And if we calculate the energy contribution due to the attraction from all the other particles, then we should first of all multiply this term, which was calculated for a single particle, by n, and we have to divide by 2 because we should not count all the pairs double. And so then we have this, and now taking this integral divided by 2, we call that a. We call it minus a because it's a negative contribution. Then we see that we arrive at minus a n squared in the large n limit divided by v. And so in the integrand we have an extra contribution e to the power beta a times n squared over v. So that should be included into the calculation of the partition function. And in that calculation we now look only at the v-dependent terms. So there is one term which is due to the excluded volume, and there is another term which is due to the attraction between the particles. So that contains this number a. Then if we calculate the free energy, neglecting those terms, we see that we have this result. We just multiply by minus kBt, and then we can calculate the pressure, and the pressure is minus dF dV at constant t and n, and we find that the first term gives a kBtn divided by V minus nb. So imagine there would be no attraction, there would be no excluded volume. Of course, I recover the free energy equation of state. But now there are corrections due to the excluded volume and due to the attraction. And now if I can write this equation in a more familiar form, which is this form here. So in this form we recognize here the reduction of the volume due to the repulsive interaction, and then we have also a correction to the pressure, which is due to the attractive force. So if the particles in the gas attract each other, they reduce the pressure. So now we consider the interesting question when we find an equilibrium between the gas and the liquid. And an equilibrium means that particles can jump from the gas to the liquid and vice versa. And that can only happen if the chemical potentials of the two are the same. So mu liquid should be mu gas. And now recall that the mu is the same as the Gibbs free energy divided by n. So that means that the Gibbs free energy of the liquid should be equal to the Gibbs free energy of the gas. And so that condition should be met for this point relating to that point. So let us calculate then the difference in free energy when we move over an isotherm from this point to this point, and then we require that difference to be 0. So delta G is the integral over this curve of dG. If we calculate dG, that's minus S dt plus V dP, but this curve is an isotherm, so that means that the dt is 0. And so we are left only with the VdP. Now in this case the P is the vertical axis, and in this integral it seems more convenient to use it as a horizontal axis, which means that we just flip over this van der Waals curve. It now gets this shape, and now we should calculate this integral, which is a bit delicate because it's a multi-valued function. So first we go from here to there, then we pick up exactly the integral below this black curve, and because we are going in this direction we get this surface area with a minus sign. Then we traverse this part of the curve, we pick up again the same area, but now with a plus sign, so that cancels, and we have in addition the area here under the curve, or right of the curve. And this is done the same, so what we are left with in the end is the blue area. And it works exactly the same for the second part of the curve. So what we should find, if this is really 0, is that the blue area should be equal to the green area. They are opposite in sign, and so their values should be equal in order to have the free energy difference vanish if we go from here to there. And this condition, this equal area prescription, that is known under the name Maxwell Construction. Finally, it is interesting to see whether and how we can transform this integral that we just did into this integral where we have P on the vertical axis and V on the horizontal axis. And the way that works is as follows. We have an integral of V dP, and we can write the dP as a dP dV at constant n and t. They are kept constant throughout the integral, and then we multiply that by dV. And so if we now perform a partial integration, then we first get a Vp, which is evaluated at V0 P0 to V1 P0. That means that the P is constant in this case, and we just multiply by the difference v1 minus v0, and then we subtract from that the p dv. So now we have here an integral that we can understand when v is the horizontal axis, and then we see that this integral gives you the red area plus the blue area, which is the area under the curve. However, the previous term was this fixed p0 value and multiplied by the v1 minus the v0, and so that's precisely the red area. So this is blue area plus red area, and here we subtract the red area. So you see that you can choose whether you perform this integral in this way or you perform it in that way. Anyhow, to conclude, the van der Waals equation of state, it's kind of a hand-waving argument which leads to its form, but it contains all the essentials of an ordinary phase transition between a liquid and a gas. I finally want to point out this region where the two minima, when you go up in temperature, they move closer and closer together, and then in the end the minima disappear as being minima. And so that is this point, that's the critical point, and in later movies I will go extensively into critical phenomena.